There we go. All right, should be good.
All right. Happy to wait if anybody needs it. Good, we're good. Okay. That's fine, that's fine. Mostly, I mean, I have the slides here in case you want to look at it later. There's a lot of links and resources and stuff in here. So, you know, if you just want to hold on to it for another time, there's also a bunch of kind of interactive elements. If you want to kind of play along with stuff while I'm showing it off, you know, I thought it might be something people want to do. So, yes, without further ado, just get that here. Okay. Let's see. So, obligatory about me slide. I am not a game developer professionally. This is just one of many things that I do kind of as a hobby, making robots, making board game design, trying to write a novel. Lots of things I never finish. This is one of them. You'll realize why very quickly.
Sorry to interrupt.
Can okay.
Step in real quick.
You can. I don't know. What I do?
No, it's
not streaming.
I get some.
Getting something. Oh, there we go. I think I'll be fine. All right, cool. No, I was just making sure.
Okay.
Sorry.
All right.
It's OBS's fault. It's not yours.
So for me, when I got kind of started saying, hey, I want to make a game, you know, I kind of looked around how do you get started. All right, there's game engines. Let me do something. And all of my instincts as a software engineer, because that's what I actually do, I hate just using tools that I don't understand, especially graphical editors. You know, I want to get in the meat of it. So I always want to look under the hood. I want to figure it out. I tend to write a lot of stuff from scratch just so I learn it, even if I throw it away later. And this is a little bit of that adventure that I took, so you know you don't have to, I guess, and maybe get something out of it. Just curious about people here while I talk. How many people here have actually like made a game that they feel like is a complete game? All right. How many people here are comfortable with programming? Because there will be code in this talk. I don't know how much. Okay. How many people have written any collision detection logic, like as opposed to just using the out-of-the-box stuff that's there? Okay. And how about JavaScript? Because that's the code that you're going to be seeing. Hopefully, it's easy enough. It's not super critical. It's most of the code I will try to go through in a way that is really more about the algorithms than about JavaScript. But I will keep that in mind. This is not a JavaScript heavy crowd. I don't know about the rest of you, but you know, again, when I come at it, I'm like, hey, I just want to do something simple. What's really popular? Unity, or you know, something like, you know, Construct 2. I know is a popular one here. What do I see when I, you know, sit down to do it? Look at a tutorial, get started. And again, you know, this talk is kind of about collision detection, but you know, let's see, this is sort of what you see. So this is like a tutorial of something you might see online. I don't know how easy it will be to see it, but basically it's a lot of drag and drop stuff. Now, not everything is like that, but some things are. They're trying to be beginner friendly, and so you see stuff like this, you just place the blocks down, and then they go through and they modify behaviors of things. This is not code. This is pretty separated from, you know, like the logic under the hood. And for me as a programmer, as a software guy, I cringe when I see this stuff, but I'm sure it's really approachable for other people. You can see they basically added properties to these things to say, hey, This thing has, you know, certain kind of collision. This thing is a platformer object. This thing is, you know, has box collision or something like that. And then poof, you let it go and it does its thing. Amazing. So this is construct 2. Oop, did not want to do that. And here would be Unity. It's very similar. There's a lot of this stuff across the board that's pretty similar. This guy's explaining it. So this is inside of the Unity editor. Again, more dragging and dropping, more sprites and boxes. Anyone who's started to learn to, you know, make games has probably run through exactly these types of scenarios. And again, they're, you know, it's all through the GUI. You're adding components that they'll be doing this thing. So, you know, to start with, you drag it out. It doesn't move, it doesn't fall, it doesn't have physics. So, you know, he's going to go through and he's going to click on these objects basically and say, here, I'm adding a component to this. I'm adding, you know, physics behavior.
Collider today.
Or a collider, box collider for collision detection. And that adds this behavior to these things. And for me, again, someone who likes to look under the hood, this is so far away from the way that I think about software and think about games. It's a big challenge for me feeling comfortable sitting down to something like this. Because I'm really comfortable with programming and understanding how things work. And this felt like, you know, trying to take something and just like learning Unity's way of doing something. You know, for myself, I looked at all this stuff, I'm like, I don't want to do this right now. Maybe someday I'll do Unity code, but for me, this was a tough sell. And that's not to knock it. A lot of people who aren't 12-year software engineers, this is probably way more comfortable for them. But it really separates you away from what's going on under the hood and how collision detection works. So you can see basically they're adding, you know, rigid body physics. It has gravity and that kind of thing. And once you've added those pieces in, you got those components hooked up. Yay! It falls. There's gravity. It lands on the box. Doesn't go through the box. So we basically saw pretty much the same thing in 2 different engines, configured in almost the exact same way. All right. So this is the code-free approach. Anyone who's not comfortable, you know, this with programming, this is probably something that's really helpful. For me, it was tough, but as you can see by the warning, I'm not a productive person. So, you know, don't necessarily do it the way I would do it, but this is why I go down this road and have literally never really finished making a game, but feel okay talking about 2D collision because I spent a lot of time building my own code to do it and looking at what other people do. And, you know, again, for me, I really like understanding these pieces. So, you know, I don't know. You know, other people with more experience may find that, you know, not understanding these things, you know, from the bottom up has maybe made some things difficult. One thing that I, as a software engineer who's had similar situations, not necessarily in games, when something has such a black box sort of abstraction, oftentimes what that means is that the easy things are easy. But as soon as you want to deviate from what is easy to package out of the box, now you're trying to scratch your head and figure out what the heck is going on because it's presented to you in a very specific sort of way. You got to find the right Unity tutorial that tells you how to do a certain thing. So, you know, my approach, I want to understand it. How would we go about doing this from scratch? And so, that is a little bit of this talk is basically going from nothing to what is the abstraction and how are those pieces presented in a way in these game engines. So we saw something that was so graphical that there's really no programming at all. But what if we had none of that and we started from scratch? So to really understand that, I wanted to talk briefly about the basic game loop. Looking at something like Construct 2 or Unity, they went through that whole piece of configuring all that stuff, and the core notion of a game loop is not even present. It's not even there. Where, depending on the game engine you use, or the types of tools you use, the game loop is front and center. It's the whole heart of the beast. And so in order to understand where collision detection is and the handling of that, and how that kind of works, you really have to understand what the game loop is, the basic cycle. Every game engine, every game that has ever been built has had a game loop at the heart of it. It's just not always really visible. So basically, a game loop is just, by a loop, it just means every frame of the game. You know, it has to check for any user input, use the combination of that input and the game state that's already in the game to then update the game, figure out what's going on. If you're controlling Mario in a Mario game, you know, you're hitting the button right, that's the input. It means Mario needs to move right, but everything needs to update. The Goombas need to move. If you're jumping, it needs to start moving Mario to be jumping, whatever. And that is also right where the collision detection is going to happen. Because when things move, they may collide. And the resolution of that collision is going to happen there, right in that update. And you have to get that update fully figured out before you can draw it to the screen. Because if Mario jumps up, you know, he's going to wind up putting his head through a brick. You don't want to draw it with his head through a brick. You want it to be in the correct spot. You don't want him falling through the floor. You want him stopping at the floor. So I've got some basic examples. Here's where it gets a little interactive here. This is just a really quick code sample. I don't know if everyone can read this, but basically, you know, I know not everyone's comfortable with JavaScript, but I mean, this is the most basic kind of conceptual game loop that draws things to the screen that you can have. You know, don't worry too much about all these variables and stuff. But basically, we have a canvas on the screen where it's going to draw. This set interval function basically just means do this every 10 milliseconds. It's going to call this function to draw. The draw is going to do some drawing operations. And it's basically just going to move this square. It's going to draw this square. These are some draw operations. And then it's going to move it. It's changing its X and Y coordinate and redraws the screen. This is just the most basics of animation right here in the basic draw loop. There's no collision yet, but just to start from the very basics. Oh, that did not do what I thought it was going to do. Hold on. How did that happen? I don't even know what. All right, hold on. Okay. Oh, it probably didn't open it in a tab. That's probably what happened. Okay. So here is something that does have some collision. So basically, it's a very similar thing. You know, it's basically the same setup, only our draw is a little more complicated. The square is bouncing around at a different angle, but whenever it hits the edge, it needs to do something. So here, we are adjusting the X and the Y by a certain amount every frame. But then we need to know what we need to do about it. And this right here, again, it's just some simple logic. You're checking the, you know, the position of the X coordinate plus the amount that it is going to move, to see if it's basically going to hit the edge, if it's greater than the width of the canvas or it's to the left of the left edge of the canvas. That's basically what this is saying. Then you need to correct the position so that it's not going over And in this case, because we're trying to make it bounce, you're changing its direction. You're saying if it was going -3 pixels, you know, it hits the wall, now it's going to go +3 pixels, and it's just swapping it. And then it draws. So it always makes sure it's adjusted itself and its state. This is basic collision detection and handling. It is detecting that there is a collision that happened, and then handling it by correcting that and doing it. But if we were to write all of our games this way, it would be incredibly tedious. Obviously, that's something that you want to be able to kind of package up. I am not familiar with. Okay. Here is one more example. So this is using a tool called P5JS, which is a library for doing kind of cool animation things. This has a supplemental library to do some collision stuff to be able to kind of make games with it. You can see this is the code for it. I'm not even really going to go through it because it's a lot. But you guys can feel free to at your leisure. But just to notice, you know, we got a bunch of these things here, and here we're starting to see some of the abstractions. Now I know this is in code; it's not through a UI, but we start seeing some things happening here, where we're basically creating sprites. We're setting colliders on them. It's not so different than what we saw in the more graphical tools. We're saying this is a circle collider. This is almost exactly like what we were seeing in the Unity demo, where they set a collider on it and they said, hey, it's a circle, this is its radius, and things like that. And then in the draw, because again, it's very similar, it's a draw loop. That's what it's doing. It's using some code to just automatically handle some of this for you. It's saying here, let's see if any of these circles are bouncing into any of these other circles. Do the collision and handling right here. This does the work for you, and then move on. But here, I mean, it's very similar code. It's basically we're changing the position and velocity. That is the basic draw loop. And so now we're breaking down. We're kind of seeing it. Whatever's going on here is a little bit of a black box. But we're specifically saying, hey, are the circles, you know, interacting with other circles? Are the circles interacting with the boxes? And we want them to bounce off them. So it's a little bit more manual. Okay. So we're seeing some of this in action. We saw, you know, a little bit of, you know, handwritten code for detecting the edges and bouncing off of them. We're seeing a little bit of library style code that kind of does the collision for us if we just ask it to. But again, under the hood, you know, jumping from that really straightforward sort of, are you to the further to the right than the right edge change, you know, getting beyond that math, that algorithm, what are the kind of algorithms that are happening in a game engine or in that library code that said, hey, make these circles bounce off these other circles. There's a few different styles that are really common in different games. One of the most common in terms of like quick and dirty, fast collision detection algorithms is something called axis-aligned bounding boxes. You know, often abbreviated AABB. And basically what this means is that if you think of everything as a box, it's very easy to take any two boxes and see if they overlap each other, thus being a collision. There are some stipulations to it though. Everything has to be a box, not a circle, not a polygon, has to be a box, and they all have to be aligned the same way. there can be no rotation, because as soon as you have rotation, the algorithm for detecting whether they overlap is very different and much more complicated. So a lot of games use this. It's fast, especially if you have a lot of things possibly colliding with each other. It's able to be very performant. So here's some quick pieces of it. So this is basically the code for doing an axis-aligned bounding box check. If you had two rectangles, what would you do? And it's basically just this right here. You're basically saying, hey, is the first rectangle's x left of the right, or the other rectangle's x plus its width? You know, you're basically, is there any overlap? It's basically just a quick math. If you know all of the sides, are there any that are overlapping with each other? You know, looking at the top, bottom, left, right. If so, they overlap. Boom. Comparatively, that's, and so here's a demo of basically this exact code working and doing something as a result of that. Circles are even easier, quite frankly, because you just know their centers, and you look at the distance based on their radiuses. So again, this is the math under the hood. It's pretty simple to do, not a lot of magic. But a lot of games, that's not good enough. A lot of games, even like a classic old school game like Mario 3 has slopes where, they are not boxes. It has to know that it's on a slanted slope, and at what point does it collide with that? And the bounding box for that cannot be a rectangle. So you start getting into some more complicated things. One that is really commonly done is something called a separating axis theorem, which I'll cover in a minute, and that has to do with convex polygons. I'm going to stop for a second. Does anybody have any questions so far? Are they following okay? Is this like a reasonable level? Okay. I just want to be meeting people's expectations for this stuff. I hope this is what you signed up for. So what happens when you need more than boxes or circles? Basically, if you have to deal with arbitrary shapes at arbitrary angles, you start having to go into something a little bit more complicated. The separating axis theorem is basically saying, are there any lines that you could ever draw between these two objects without touching them? If you can draw a line between them, they're not touching, you're good. And I have a video explaining a little bit of the algorithm because it's kind of complicated.
Hi, today I'm going to explain to you the separating axis theorem, also known as SAT. The separating axis theorem is used to check whether or not two objects are colliding. For this explanation, I'm going to use two cubes. We want to check if cube 1 is colliding with cube 2. But how are we going to do that? We're first going to get a few axes based on the normals of the edges of the cubes.
Okay. So if we were dealing with these as only axis-aligned boxes, that number 2 box couldn't be allowed to be rotated that way. And if visually it was rotated that way, because a lot of times games, you may have sprites that are not actual box shapes, but they use boxes as their kind of collision detection bounding boxes. And if we had to make a bounding box for 2 that included that kind of bottom right corner and that left bottom corner, the box that you would have would wind up overlapping, because the bottom of 2 is above the top of 1. So to be able to accurately see that there's basically a line that you could draw through here, we have to
We're going to do this step
think
by
about
step.
it in terms of their rotation.
Of cube 1. These axes are displayed in lilac. As a quick note, SAT only gives accurate results if both shapes are convex. Then we'll need the positions of the corners. These will be displayed with red circles. Since the axes are vectors and the positions of the corners too, we can use the dot product to calculate the projection of the corners onto the axes. Then, by getting the lowest and the highest value on each axis, we can calculate the projection of the cube onto the axis. The projection of the cube will be displayed with the red bar. Then, we're going to do the same with the other axis.
So we got this right here. Basically for this box, we know we got that. And then we
Then
project it over here.
We also have to project the other cube onto the axis.
Here. So that's basically representing this box. We've got this and this. Now we got to do the same thing for this one.
Since we're using the corners, we can calculate the projection of rotated cubes too.
So we know that this and these overlap according to this axis. We know that these overlap here. And then again, they're overlapping here. So these lines here are overlapping. That makes it for this one axis shows that they overlap, which is basically what we're stuck with axis aligned bounding boxes. You can see that basically if you were to draw out where it is, this horizontally overlaps with this, and vertically it overlaps with this. So if we were stuck with just axis aligned bounding boxes, this would show as a collision. I'll keep going.
You can clearly see that the cubes are not colliding. There's definitely room between them. In order to solve that, we'll have to do the same that we just did with the axes of the second cube. Since we already did the calculations, I'm going to do it very quickly. These axes are going to be displayed in green.
So the reason why we're looking along this edge is because we're basically looking at the angle of this. So these first ones that were done in red were done from the perspective of the first box. That was the angle that this was looking at. That's what the sides were that we were looking at. But for this box, you can see it's like this green is kind of rotated to match the angle that this is rotated at. And we're looking at it from that perspective now. So you can see this is...
Now you can see the two of the projections are not intersecting, which means
basically
no
this
collision.
line going over to here and then this one going over to here, according to that. So I don't know if that made sense. Hopefully it did. And again, not expecting anyone to come away with this, expecting to implement these algorithms necessarily, but okay. One thing, and again, I can easily cut this. I don't know how much people care about digging into code. I'm a software guy. That's what I like. There's not a ton here in terms of programming, so I'll kind of go through it quick. But I'll start by just looking at this, which isn't actually looking at the code. But this is an example of a library that you could use. Hypothetically, if you didn't want to use a full game engine, but you didn't want to write the code that was just being described in that exact algorithm, this is, for example, a library that one could use that would do that kind of work for you. And you can kind of see the way they break it down is kind of interesting. So they have, and again, some of these terms you may have even seen them in games that game engines that you've worked with. I mean, these are pretty, these are like the basic core kind of entities for any kind of algorithm like this. A vector is basically a point. A circle is a circle. A polygon is a polygon. Just meaning that it could have arbitrary number of sides. For the constraint of separating axis theorem, it has to be convex shape, meaning that you can't have parts that kind of dip axis aligned bounding boxes. The code gets a little more complicated. It's a little less performant. But it's pretty good. I mean, this is a pretty solid algorithm for doing this fairly quickly. It's just a little more complicated. The code for it, I will go through quickly. If you guys were really code people, I would do more. But let me just skip down. This is, so if anybody wants to implement that, and you just coded everything from scratch, stepping forward, seeing the kind of tools that are available to like step into doing these collisions. How do they work? What do they do? If we were to write these abstractions ourselves, if we were to package up and create our own game engine, you know, to say, hey, you know, you start from scratch, you're not going to want to write that same boilerplate code over and over again. You're going to start packaging that up into classes and functions and libraries and things that you would use yourself. It would start looking something like this. These examples are all from a web-based game engine called Phaser. It's a little more code-oriented than Construct. And it's actually pretty cool because, for example, you can full-on, it has like a browser-based editor you could even make games in and stuff. So this is like out of the box if you wanted a platformer, right? This is like the basics. It looks so much like the other examples that we've seen. You know, I can jump around. It collides with things. And what is that like? So again, and again, I don't know everyone's experience here, but I know for me, it really helped when I first started approaching games, really trying to understand, again, the game loop. What are all of the phases of operation that are happening? To make it go from something that seems so black box and so abstract into something that's more concrete. So the way that they break it down here with Phaser, I think is actually a really nice way of understanding it, the way that they break these tabs down. So it's loading up all of the stuff that it needs. It does this one-time creation stuff. And here you can see it's kind of interesting. They have basically arcade physics is what this is called. They have multiple physics engines that you could use depending on the type of thing you needed. And in this case, the arcade physics is basically axis-aligned bounding boxes. So, you know, again, not so different than Construct. You're basically saying here, this player is a physics-enabled object. If it collides with the world bounds, right, that automatically gets it so that if it touches the edge of the screen, it'll stop. We've added gravity. All this stuff should be looking kind of familiar. And then it's creating these platforms, which are immovable. So they are part of the physics system, but they are immovable objects, so they won't fall. And then in the update, it does this collide function. I mean, this is like we've packaged up collision all the way just into this one thing that does it all for you. We want to see if the player collides with the platforms. Using this particular function automatically kind of does the handling for you in terms of, you know, there are different functions like overlap instead of collide. Collide specifically tells you how you're going to handle it by saying, hey, if these two things are going to overlap, I want them to not overlap after we resolve the collision. We want to make sure there's no way they're allowed to be in the same space. So that makes it so that the player stops when it lands on the platform instead of being in the platform or something like that. And again, this is our code that makes things move. This is very similar to what we were seeing in the from scratch kind of mode of the game. It's basically just changing the position of things. And then yeah, that's what it winds up with. I'll toss out a couple other things. So that's kind of the code I wanted to walk through it. But again, if you have different kinds of scenarios, you may need different kinds of collision. So this is a basic arcade physics example. Again, that's the sort of axis-aligned bounding box approach. These are the bounding boxes. Boom, they touch. Yay! And again, it just kind of comes down to let's see, in this one, it's the update function. So this is basically draw. In the case of Phaser, they call it update, and again, it's just doing this collide function. And in a lot of games, you can add an additional handler because you want maybe to do something when they collide. You want to do more than just make them stop from overlapping. You want them to actually do something, so you can set basically a callback for what it's going to do. In this case, it made the background be red. But what if you need more than axis-aligned bounding boxes? Here's an example of a slope. Classic. So this couldn't be done with axis-aligned bounding boxes. This is going to need to start doing something more along the lines of that separating axis theorem stuff. It needs to know because, you know, when it's here, I'm trying to make it touch. When it's almost there, you know, like, because this, you know, if this was a box, it would have to be here too. And it would bump into it here, but it doesn't bump into it until it actually hits it. And so in order to do that, you basically have to imagine that line that would go through separating axis theorem that until it actually gets all the way in, it hasn't touched. So you don't need to see the code for that, but that's just the difference. And then we can go crazier than that. You know, and this really doesn't even change collision, but sometimes you need to go a step further and have a whole separate physics engine. So like there is collision detection happening here. There's a lot of stuff going on, but once you start going to the point where you need physics, you know, it's a whole new ball game. Like there are so many operations that it has to understand itself. It's kind of hard to get away from it being a total black box because these things get super complicated in terms of, you know, having things like this chunk of the chain is attached to this chunk of the chain, and how is it going to rotate? How is it going to stay connected? Things like friction and spring coefficients and things like that. So one thing to note, because there is more to this story. Even with all the things that I talked about, even with something that's as simple as axis-aligned bounding box collision, by the time we got to the sort of abstraction of it saying, here, check to see if all the circles collide with the other circles. What does that mean? What's it really doing? It's basically going to wind up taking every circle in those groups and running that check against every single other one, which sometimes is exactly what you need. But if you were to have a game, for example, that had like bullets flying everywhere and asteroids flying everywhere or whatever, you start hitting this sort of exponential growth of how many of these collision detection checks you have to do. And without being smarter about it, it can really bog down the performance of the machine. So something that is generally always talked about when you're talking collision detection, there's collision detection that's dumb and there's collision detection that's kind of smart. And you kind of have to get smart. I mean, depends on the game, but at some point you probably will need to. So, I mean, the sort of obvious thing that you know, to start with, and we can see this, not every object that could collide with something belongs to the same group. You don't necessarily always care if, you know, especially something like tile system. The tiles never move. They're never going to collide with each other. So you don't have to worry about checking tiles against other tiles. That's when you can start creating collision groups. Now this is something that maybe you guys are more familiar with, because that concept is typically up at a higher level that people using a game engine would care about. But here's an example of groups. This is important for both game logic and performance. Let's see, I think this is, oh shoot, clearly not in the game. So there's, we're blasting vegetables with lasers, because, you know, that's what you do. So, you know, we don't care about vegetables colliding with other vegetables, and we don't care about bullets colliding with other bullets. So one way automatically to make both the game logic easier and more performant is to break those into two separate categories of things. And so you can see, you know, you kind of have a group for bullets and a group for vegetables. And then, let's see, where is the collision? Here we go. So we're checking, in this case, we're checking for overlap. So we're checking to see if the bullets overlap with the veggies. And that overlap function, basically, the difference being is that it's not going to make the bullets stop when they hit a vegetable. If it's going to keep going through, it's not actually going to resolve that collision by adjusting any positions. It's just going to do this collision handling, which makes the vegetables disappear, basically. Let's see. But that's not enough. Sometimes you need some serious stuff going on. So basically, any game engine worth its salt is going to do collision in the way as described here. This is a really good article, by the way. I don't know. I mean, it doesn't go over a ton, but I like it. Collision performance is usually done in two phases. You have the broad phase and the narrow phase. The broad phase is basically just is basically saying, hey, look, you know, the bullet that's way over on the left side of the screen is never going to wind up hitting the vegetable on the right side of the screen. Rather than have every bullet check every vegetable, what if we could just quickly narrow down which possible vegetables it would be hitting before actually running a potentially expensive collision detection algorithm on it? And so there are certain kinds of algorithms, quad trees being a really common one that I was going to go into. Basically let you break down the possible collisions so that the actual collision detection is a much smaller list. So that's broad versus narrow. And I'll give you an example of that. So here is a little bit of an explanation of quad trees. I'll skip down to the relevant bits. If you take if you take the game screen, it's called quad trees because it divides it into 4. Basically, every time something that may collide gets put on the screen, it gets put into one of these boxes. So boom, all right, these things belong to this quad, these things belong to this quad, this belongs to both because it's overlapping. But at some point, if you have a lot of things, that's not even enough. So it'll take a quadrant and divide it again. That's what makes it be a tree, if you're familiar with data structures. There's a really cool demo, though, that shows off what this means if that was pretty foreign to you. These boxes are showing the quad trees as they're getting made. So you can see as things are leaving this quadrant, it's just the one box. But in here, where there's a lot of stuff, it's getting broken down again. And here it's getting broken down again. And typically quad trees work that way. It basically says how many things can be in this quadrant before I break it down into another level deep of quadrants. So that's that. So that basically that means that by dividing it in that way, maybe I'll go back to the demo for it. Dividing it in that way, for example, if these things can bounce into each other, well, they actually can. It's really just with this guy. So this guy's basically seeing which ones can it bounce into. And if you didn't use a quad tree, you'd have to check every single one of these things. But by virtue of it being in a quad tree, whatever quad it's in, it only has to check the other ones that are in that quad. That breakdown, even as deep as it is. So if this thing was in this box here, it doesn't have to check everything here. It doesn't have to check everything here. It just has to check this one little thing. So that's like 3 of them right now. Keeps it moving really fast. And pretty much, seriously, any game engine worth its salt is already doing that. But I guess some naive implementations might not. So detection is only one half of the problem. I am more than halfway through the presentation, though, I promise. The handling is another piece, and actually it's really fascinating. When I was first digging into this, it's interesting, depending on what library you're looking at, depending on what code you're looking at, it can be a surprisingly tricky problem. Because depending on the information that you have to make different kinds of assumptions about how it should resolve. So the most basic thing that we were seeing in those phaser examples, we saw two different kinds of collision handling. One was overlap and one was collide. Overlap did not adjust the positions of anything afterwards. If they overlapped, they stayed overlapping after the collision. They were just drawn that way. Usually, you know, a vegetable would disappear, so there's no overlap because of that. But isn't doing any adjustment afterwards. The collide algorithm, though, that makes it so that, you know, again, the player standing on the platform doesn't fall into the platform. And that means that even through the update step, which calculated new positions, the new position that it calculated is partway into the platform. Before it draws it to the screen, though, it had to adjust the position of that player sprite back up to the platform so that it wasn't falling into it. And that additional handling is sometimes tricky depending on what you're doing. I teach programming to kids on the weekends sometimes, and we do a little bit of game development stuff. We use a tool called Game Maker, and what's funny about that is there are literally dozens of videos online for how do you do collision handling in Game Maker, because they give you some of the tools but not all of the tools. They give you the tool that says, hey, did anything here run into anything there? But it doesn't give you the out-of-the-box thing to say, don't fall through it. So there's literally like the top tutorial on how to do this handling in Game Maker basically says, if something runs into it, move back and then move one pixel at a time until you don't run into it anymore, which is pretty much the least efficient possible way of taking that step back. Imagine if you have hundreds of things that could be colliding in that way, running that same iteration over and over again. And usually it's small amounts. I mean, your frame rate's high enough, you're never going to move more than a few pixels, but still, it's a really inefficient way of handling it. And by not giving you the tools out of the box, it creates a weird challenge. Let me see. So that's the problem. And so you wind up kind of making these assumptions about what does it mean, in phaser, how do they figure out what are they doing under the hood when they do that collide function? How do they know how to step it back? If they know it's overlapping by 5 pixels, sometimes you have weird edge cases. I basically implemented a collision detection and handling system myself, and you want, especially when you're doing something like a tile map where everything's a bunch of tiles, what happens when you're colliding with 3 different boxes at the same time? How does it know which directions to move back? You can't just look at one box and say move it back 5 pixels, because then it might run into another box in a weird way. Sometimes that stuff can be weird. I'll just show this one again. So we saw with this one, we got a whole bunch of things moving, and we've got in our draw, we do this bounce function. And again, I know not everyone is like a super programmer, but if we jump into the code here, and again, if you want to write your own game engine collision code, you know, this is par for the course here. But what's going on in this bounce function? Let's see. I'll jump into it here.
I'm sure this is exactly what you learned during your master's for your
Physics, I added other stuff.
So it's interesting, and one of the things that actually this brings up, which is like, it's one of those things that's it's trickier than you might imagine, right? So the way that this bounce function or the collision function in phase or whatever they're trying to do, what it wants to do is basically say, hey, if this box over here is overlapping with this box over there, just make it go back in the opposite direction, or really what it tries to do, actually, you can, well, actually, I don't know if this is the right example to show it. Really what it tries to do is it tries to, oh no. This is the thing. Really what it winds up doing, if you actually look at kind of the way the algorithm works, is so you got to imagine, you're not seeing the overlap because it prevents you from seeing it. Before it draws, it corrects it. But like this thing is trying to bump into this box. If we didn't do that handling to pull it back, it would just kind of like overlap by a little bit there when it does it. And what the algorithm is doing under the